and available later after this on my website. And we can talk about putting it elsewhere if IEEE wants to do that as well. But we will have it posted probably by next week at this point. And let's see. Again, I want to thank IEEE for teaming up with the Northeast chapter to make this possible. And looking forward to the discussion. We've got a lot of interesting things to bring forward, and I'd encourage you to ask questions as we go. I muted everybody to start with, but you can unmute anytime you want to ask a question. I'll keep an eye on the chat, but I may not be able to get to all of them at this point, but certainly if you want to speak up and ask a question, that is more than welcome. And to get started, I just wanted to tell you briefly about my team. We have a team of great friends that we've been friends for decades, great scientists, and have a very broad range of expertise, not only in manufacturing and but also in design, product design, hardening for ESD. So we have some unusual skill sets there that are really powerful. And I know many of you know us well. We provide strictly professional services and do not sell any products on my team. We've had many very interesting engagements around the world, and I'd love to tell you about all of them, but time doesn't permit. And some really fascinating things that we've enjoyed over the years. Now, let me just see if everybody has been admitted so far. Looks like we're in good shape. So let me get started with the presentation. So today we're going to be talking about S2020 and the upcoming changes, the 2021 changes, what's new and what's missing. And some of the things that are missing are understandable. I mean, it's not intended to be everything for every application. But let's get into it. And here we go. This is the outline, and we're going to step through these one at a time, so I'm not going to dwell on it at this point, but get right into it. Here are a few acronyms or abbreviations that we'll use today, and I just wanted to give you a look at it ahead of time. DA is for my company. SRM is for surface resistance measurements. ESDS is ESD sensitive products or items. And CV is for compliance verification. And then these acronyms here, I expect, are familiar with all of you. But you can see we'll be getting into the human body model, charge device model, charge board event, cable discharge event, and electrical overstress. Okay, now a few introductory thoughts. Something you should know or will find out before long is that JEDEC 625 is being updated and is expected to be released in 2022. Terry Welsher and I were both on the committee that helped do that, and you'll find with the new release that some of the items that are missing from 2020 will be in JEDEC 625. We also have the IEC version of S2020. This is the European version of S2020, and it very closely parallels our S2020. The mill standard 1686 has been canceled as of January of this year.
Hey, Ted.
Yeah.
This is Gary Collins Aerospace.
Hi.
Hey, hi. So you just mentioned that the IEC standard parallels 2020. Would you say the same thing about JDEC 625?
Well, there are a lot of similarities. I think there are the formatting of it is different. It's an excellent document, but it's different, but includes most of the same concepts. So in that sense, yes, but not as closely as the IEC standard. It's in many ways almost identical to 2020.
Okay. Would you say that 2020 is stricter requirements wise than the JDEC 625?
No, it's probably the other way around.
Probably the other way around. Okay, thank you.
Yep. Okay. Now, S2020 is a basic level of protection, and it covers a broad range of applications and is generally applicable to most operations. And we'll get into it in more depth as we go. It has been widely accepted internationally, and as you may know, it has replaced 1686 and has been recognized by the FDA. It is specified by most OEMs, and most contract manufacturers use it as well. It is also ISO 9000 compatible. It also comes with facility certification. And of course, that adds credibility to a program, and the accreditation or the certification can only be performed by ISO bodies. So in other words, consultants or other entities are not able to perform a certification. They can help prepare for it, but they're not able to do the actual certification. There are over 1,000 facilities that have been certified, and with the introduction of the changes or this new issue, each of you will have that are certified will have a year to comply with the new issue of the document. Arnie, I made you a co-host, so if you could keep an eye on people coming in, that would be great. It is, as I said a minute ago, compatible with most existing programs, both technically and administratively. The limits tend to be broad limits for good reasons. It can be tailored, which is one of the many strengths of the document. And there have been some enhancements to the tailoring information. Okay, let's get into what is new. Just a second here, I'm checking something out. Okay, good. Okay, so let's get into what's new. In fact, this, let me go back here. 1, 2. The slides that are white like this with the ESDA logo are association summaries of the changes. John Kinnear has done this a few times, excellent presentation, and I encourage you to get his presentation of it. But I just wanted to make sure you understand that that's where these white slides come from. And this is a list of the major items that are in the new version of 2020. some new definitions. The tailoring has had clarifications, and product qualification. There have been some major changes that we'll talk about. Compliance verification, no specific changes, but there are some other things that influence the compliance verification, such as packaging. The other major items are clarification for the grounding and bonding. It's only required for initial verification during the original installation. In other words, compliance verification of the grounding system is not a requirement. Insulators and additional options for measurement have been included that we'll share with you. Isolated conductors. There are some changes here of interest that include measurement reference techniques. Table 3 has had slight changes. Packaging, there are significant changes here. It's been added to the compliance verification. That's one of the big changes for that. And an additional table, table 4, has been created. And the DoD requirement that you see here, 2073-1, has been added to 2020. Marking, excuse me, has been clarified and an additional reference. There are some really excellent tailoring examples in Annex C. There's been some confusion over that in the past, and that Annex C goes a long way toward clarifying. And then Annex E includes a statement of direction that we'll talk about more shortly. These are the definitions that have been added to 2020, all related to this document. I'm not going to go into them in detail now, but they are there for a good reason and will apply to 2020. Product qualification. This is an area with significant change. The change to the product data sheet is highlighted here. Objective evidence for the qualification shall include the test report, not just the data sheet. In the past, the data sheet alone was sufficient. Going forward, you'll also need test data. However, this applies to materials that become qualified when this 2021 version is adopted. Requalification of existing items is not necessary. There's been questions over the years about relative humidity, and what this now allows for is to qualify at the lowest relative humidity at your facility for the items that remain on that facility. For example, it does not apply to packaging that leaves the site, and it does not apply to other sites within your company. But it does clarify the situation where if you live in a high humidity environment, that tends to be forgiving, and you can go with the relative humidity that you experience at your facility. And then clarification on product compliance verification data and how it can be used. For instance, footwear and flooring resistance is not evidence of qualification. Insulators, this is always a hot topic. It was during the committee discussions, and I expect will continue to be. And it's a difficult one. There are a lot of variables to take into account. What has been added is a new measurement alternative. It's now possible to measure the field where your ESD item is processed. So this is a significant additional measurement opportunity. And at that location, the potential must be less than what you see here, 5,000 volts per meter or 125 volts per inch. The field is can be measured the field can be measured, or the insulators can be measured. That's what this is getting at. We're talking about making field measurements directly at where the product is located or on the insulators that are of concern. It allows for non-essential insulators to be within the EPA. This is typically for materials that are very difficult to keep out of the EPA. It might be incoming packaging for non-ESD sensitive items, as an example. And yet the requirements around ESD sensitive items still have to be met with this change. A note has been added regarding the use of field meters and non-contact electrostatic voltmeters. There are many, many ways to get misleading information from making field measurements. And with the different meters, they each have their own characteristics, and it's very important to understand what they are and how to use them. If you're interested in more depth on that one, there is a video on my website that explains the differences in some depth. Here is a illustration of the 2020 requirement. You have a requirement at 1 inch, and you have another one at 12 inches. Namely, if you have an item that's charged and it's less than 1 inch away, it must have a potential of up to 125 volts or less. So in other words, it has to be less than 125. If it's over 2,000 volts, it needs to be kept away the 12 inches, which leaves this middle zone with a little bit of concern. And here we're talking about, what we're saying is if insulators are between 126 and 1,999, the concern here is that if it's greater than 1 inch, the mitigation is not required. However, you know, with manufacturing, changes happen all the time that can influence this. So what the new requirements bring is a new concern. Measurement of field where the product is being processed will or can be compromised by voltage suppression. Field on the product is subject to handling variation as well during processing. So there are a lot of variables that come into play in daily activities. The voltage suppression and the limitations of the meters that can be used, the field meter versus the electrostatic voltmeter, need to be taken into account as well. Very important to, again, to re-emphasize how to make these measurements correctly. Now I'm going to do a demonstration for you of the concern here. And bear with me. I'm going to show you the desktop here. We have the grounded mat I'm going to put my wrist strap on like so. And what I've set up here, I have both meters here. And I'm going to turn them on. This is an electrostatic voltmeter. This is the field meter. And here we have a static generating material. And here we have a circuit board. Now I've placed it on an insulator that I have previously neutralized. So the insulator is not charged. I did that because this board has conductive elements that run right down to the mat. So in other words, if the board is grounded, that changes all the dynamics dramatically as well and protects the board well. So for this demonstration, I wanted to illustrate the board being isolated as it might if it were resting on insulating components like transformers. And what I'm going to do now is I'm going to measure the circuit board first, like so. And here you see we're measuring just a couple of volts, very, very low. Now I'm going to also measure the static generator. And I'm going to measure it here. And whoops, I pushed the wrong button, sorry. Let me go back and push the right button. Okay, there we go. I'm holding the reading that I just got, and we're getting 28 volts on this insulator. So if you measure it here, voltage suppression is going to reduce the potential by that mechanism. To illustrate that, I'm going to lift the item off of the bench, off of the mat, and retest it. And now you see we're measuring almost 1600 volts. So this is really charged to a high level, but laying on the mat, as one would expect, voltage suppression greatly reduces the reading and the risk, of course. In this position, there is minimal risk. And the board is still at a low charge. Now what I'm going to do is I'm going to bring this over near the board and measure it again. Now this time, I'm using the electrostatic voltmeter intentionally at some distance from the source. And here we're measuring 109 volts. Let me just try it again. Sometimes I get a higher reading when I do this. Right now I'm getting 128 volts, which is over the 1 inch limit. But more importantly, this is a circuit board, and a circuit board charged to 100 volts is in much greater jeopardy than a component at that level. A component at, and I will get into that more in a few minutes, so I don't want to belabor the point. Now, to illustrate the field meter complication, I'm going to bring this into view. And I'm going to do the same thing, and I'm going to try to keep the field meter as far away from the measurement as I can. And with this instrument, measuring it much the same as I did with the electrostatic voltmeter, we're getting only 44 volts, which is one of the reasons we recommend using the electrostatic voltmeter instead of the field meter. The field meter has a large measurement area, 4-inch circle. So when you bring it over here, as I did, it also includes the ground potential of the mat, which lowers the reading. Whereas the electrostatic voltmeter has a very small spot size, a few millimeters. And therefore you can measure the board with, in this case, with a much less influence of the voltage suppression. That's not always the case, but in this particular example, it is the case. Okay, so that's a concern. And having grown up in manufacturing, I know firsthand how easily things change from day to day, moment to moment in a production line. I can tell you all kinds of horror stories. Okay, so
Hello,
now, Yeah,
Hello, Ted. It's Man here. I'm calling from Canada here.
hi.
The test that you just performed and so far I've read there is no factor in terms of temperature and humidity. How important is that with when conducting that kind of test without temperature and humidity?
Well, the measurement, the instruments will report what they are detecting, what they're measuring. And the environmental conditions can influence the level of charge. You know, if you have high humidity, the charging level on these items will typically be lower, but takes time to get there. So they can influence the temperature to a much lesser degree. Temperature is not a big factor, although it does influence relative humidity.
Right. Yeah.
So
There's S2020, the new one that the one to be released there. Have anything, any discussion about humidity then?
just what I mentioned earlier, that you can qualify your products based on the relative humidity conditions in your building. It was removed from 2020 2 issues ago.
Yeah. Okay. All right. Thank you.
You're welcome. Thanks for the question.
Hey, Ted. Hey, Ted,
Yeah.
this is Matt Strickland.
Hey, Matt.
Hey, just for the group thing, I mean, I know the answer myself, but for the group, is there any, do you gain anything if you use a contact voltmeter versus the electrostatic voltmeter during that measurement?
Contact voltmeter has its own properties that you need to understand for using it. In the example that I just did, it would allow you to make direct contact with the circuit board at a specific pinpoint location. However, it's not as effective measuring insulators. So it has its limits and strengths. Is that how you would have answered it, Matt?
Yep. Good.
Thanks.
Yeah, there's from my mentor. Yes, sir. Thank you. I just wanted to clarify. I know I've got a new guy that's on the call here, and I'm trying to get him trained up as well. So that's
okay.
Thank you for verifying that for me.
Sure. No, thanks for the question. Another concern is that often high-risk insulators are part of the product itself. And, you know, we've been to a number of clients that hadn't really thought about that. They were very carefully looking at insulators in the workplace, you know, that come and go, but they had not fully considered the product itself having insulators. And in one case in particular, I could tell you others, but one that comes to mind is a circuit board edge connector. The edge connector was charging to significant levels. And when it was pressed into the circuit board, it was injecting, because of the floating metal pins, and you know, you have isolated conductors in this edge connector. And now you have an isolated conductor. And when it was pressed into the circuit board, it injected a transient that was damaging ASIC device at a very high failure rate. So be aware that insulators are on the board itself as well and need to be managed. And often you have to go with ionization. Sometimes there are other better approaches. In the document, in 2020, it states that insulators should not be artificially charged. And there's been a lot of discussion about what that means. But the concern that we have is that the charge on the product will vary, as I showed you in the demonstration a few minutes ago. So you need to be very careful of that, and we'll give you some recommendations on the next, coming up shortly. Another concern is that ionization as a mitigation method in the insulator section or set of requirements in 2020, the ionization has been removed. There is a note saying to go to TR 2020 for insulators, but the actual use of, actual mention of ionization as a mitigation method has been removed. And hopefully you all know that it is a powerful tool and needs to be used appropriately. Now, what we recommend is that, again, for compliance verification, let me qualify this too. If you have a third-party audit coming in, I'd just assume they don't rub anything anyway, because it is complicated. And often the people coming in from a third party or customers may or may not be well versed in what it means. Anyway, for your own management and control of the program and the compliance verification, we recommend rubbing the material, rubbing it with a material such as a cotton cloth. Cotton is in the middle of the triboelectric series, and it's a choice, let's put it that way, to identify and manage your static generators. As I showed you a minute ago, if you don't rub it and measure it properly with the item up in free space, voltage suppression will compromise the reading and you won't really know you have a problem. So one way to simplify this, and still within the scope of 2020, it's your option. What you can simplify it to do is to indicate that insulators at 125 volts or higher need to be managed properly. They need to be either kept away or ionized. Or if your process is set up and you are well versed in the use of ESD event detectors and you have an event-free operation, you can be sure that things are, that the process is under control. These, especially the event detectors, require advanced measurement training. There's one way I like to put it is that they're equally as powerful as they are confusing and complicating, but definitely a powerful tool. Okay, isolated conductors, very important addition to 2020. The requirement itself didn't change, but the way it's measured has changed. Instead of measuring the isolated conductor or the potential difference from the isolated conductor to an ESD sensitive item, the measurement is now from the isolated conductor to ground. Certainly a much easier measurement to make and excellent change. Additionally, if the isolated conductor does not come into contact with the sensitive item, then you can treat it as an insulator and apply the associated requirements of the field related to the isolated conductor. That also is a good addition. Note, there is a note that recommends using high impedance contact voltmeter and cautions about the other choices that we've already touched base on. Yeah, especially for this type of measurement, if you have an isolated conductor, and earlier to your question, Matt, the contact voltmeter is excellent for that. That gives you a direct measurement to ground and is a very accurate measurement. This is the table 4 that was added to 2020 for packaging, and it gives you this range of choices. And I'm glad to see it in the document. You'll see the concerns coming up regarding the use of conductive packaging. That can be problematic. And we always advocate using dissipative packaging to gain the added benefit of the current reduction or peak discharge current reductions that come with dissipative materials. Annex E, again, excellent place to go. This section is preparing the user for requirements that may or may not change in a future version, revisions to the document. It does not mean that what's there will automatically be included in the next revision. It just means that it's under consideration and may be considered in the future. Here is one of the suggestions, and that is a potential requirement to document all components, or at least inquire for the HBM and CDM sensitivities. Also, there is another thought here about providing objective evidence that your manufacturing process is capable of the limits that are documented in your plan. And that may require use of SP 17.1 process capability. Again, these are future considerations and not mandatory today.
I have one question, Ted, just to help clarify. I noticed we're speaking, about the 125 volts, HBM 125 volts on the previous slides and so forth. And what about lower than that? Like for the class 00 and 000, which is, I guess, yet to come, which takes the 125 down lower. Is that not really in the near term, or is that down the road? Or because I see that your 125 is kind of the number, right? But isn't it lower than that as we move forward?
Well, excellent question. As it stands now, you're correct. 125 is the potential in S25 for static generating materials, but we need to be careful not to confuse the various limits. And we'll get into the scope of the document and the HBM and CDM sensitivities in a few minutes, so I don't want to dwell on it now.
Okay, that's fine. That's fine. Yeah, no problem. No problem.
Okay.
Okay, thank you.
Yeah, good question though. Thank you. Okay, so what's missing? Well, some useful information has been moved to TR 2020. For instance, ionization mitigation as a method in mitigating the harmful possible effects of insulators in section 8.3.1. The other thing that is of concern is that English units in general are being omitted from all the standards. And we personally would prefer to have both included. For the people in the United States, we're illiterate when it comes to metric units. So it really is a disservice to US users of the document. 2020 intentionally does not include how to make measurements. It's not intended to be a training document. And it does refer to other documents, as you see here, and other standards for those measurement techniques. And that's perfectly understandable. There's no mention of the charge board event or cable discharge event. And those are significant risks. The charge board event has proven to be a major contributor to ESD damage. And we'll talk more about that. There are no surface resistance requirements or limits for materials that contact sensitive items for the charge device model or the charge board event. We'll discuss that a bit more in a minute as well. The packaging requirements, as I alluded to, permit the use of conductive materials, and they have their place, but anything that is in direct contact with an ESDS item, we strongly recommend dissipative materials. There are many good reasons for that. We also like to see periodic walking voltages in your compliance verification plan. It's not required, but is something that is important to keep track of and periodically evaluate. Again, there are a lot of variables there that can creep into your process. And there's no requirement for using compliance verification to manage insulators. It's not a part of the tables, therefore it's not part of compliance verification. This is a chart of a high level look at the document, and it is, excuse me, it is, there are some things showing here that are understandably not part of the standard. I mean, I'm not suggesting that all of these should be in it because it wouldn't make sense. But it circles back to the question you asked a few minutes ago about sensitivities down below, down deep into the class 0 region. There's a limit to what you can include in a document like 2020. So including all of the class 0 sensitivities is not practicable at this stage. In fact, there's a school of thought that for extreme sensitivities, down in the single digits as an extreme case, there may not ever be a standard that would give you, a cookbook procedure. Usually there is customization required when you get into that level of sensitivity, which again is another logical reason why it's not in 2020 at this point. 2020 does allow conductive work surfaces. Again, we have concerns about that. Or conductive surfaces in general. And taking that into account, the standard does still lag the technology. And again, a lot of it is for just, explained justifiable reasons. It's not really criticism as much as it is an observation. This is the scope of 2020, and what this, and we'll talk about this a little bit more in a minute, but what it's saying is that it is designed to protect product that is HBM sensitive at or above 100 volts, and for CDM at or above 200 volts. And there's also a metal object or of greater than 35 volts being an issue. However, there are no surface resistance requirements, SRM requirements in the document. And metal charged at 35 volts, depending on the circumstances, can be a high risk. So you need to understand that part of the document and how to apply it judiciously. So therefore, we advocate starting with 2020 and customizing it for these scenarios that we've talked about for class 0, charge board event, cable discharge, and CDM. Here's the deeper discussion on the scope of the document. The CDM limit is set at 200 volts, and there's very limited data that it's been based on. It's often hard to come by, so understandably, it is limited. And the 200 volt limit really applies to integrated circuits, but not so much to ICs on circuit boards. As I mentioned earlier, a circuit board charged to 100 volts can be a very high risk. And again, there are no surface resistance requirements, and we'll talk about that a little bit more again in upcoming slides. There's an important distinction to make there. So based on our experience, we have seen cases where programs that were compliant with 2020 were experiencing failures with devices in that 200 and above category. So we advocate adding surface resistance requirements. And let me just back up a half a step. When Terry Welsher and I were managing the AT&T program, we placed great emphasis on surface resistance requirements and found them to be generally less expensive than putting in a whole army of ionizers, as an example. Plus, once you have the right materials in the right place in the process, the mitigation tends to be more robust and enduring. So they're less prone to human error, excuse me, and they become absolutely essential for extreme sensitivities, especially down in the single digits. Overall, what we're advocating is a blend of surface resistance requirements and the insulator controls that are available to you. Regarding insulators at 35 volts, that's more of a requirement than a scope of the document. So we advocate sometime in the future moving it out of the scope. And to put this in perspective, if you have an object that is charged, the Q is the charge on the object, and if, for the sake of discussion, we're going to assume that it's isolated from ground, so Q will be a constant. But if the item has a high capacitance, that will mean that the voltage will be low. For instance, if you somehow had a cart that was isolated from ground, it has a very high capacity to store charge. The voltages on it will be low, yet the discharge currents from it will be very, very high. So beware of that. And the ongoing variations in handling and processes. So one way to do this is to set the resistance requirements for isolated conductors. Provide some dissipative or other means of grounding these isolated conductors whenever possible. If not, you go with the voltage measurements outlined in 2020. So work toward not permitting the voltages in the first place. Ground them. That is the ideal recommendation. Not always possible, but go in that direction whenever you can. Here's an example. This was a case study where a defense manufacturing client asked us to visit their entire supply chain to find out why they were experiencing charge device model damages to devices on boards. And believe it or not, we were very surprised with what I'm about to show you. After going to all of their sites, we found that there was a common root cause, and it was a screwdriver like this yellow-handled screwdriver that we see everywhere. It turns out that well, but I'm going to tell you a little bit more about what you're looking at. This is an oscilloscope set up with a current probe. And this is the peak current that is being measured by the scope, this transient. And in this example, the handle was at about 1,000 volts. The tip on the screwdriver was only at about 28 volts, which is below that 35 volt limit. Yet the discharge currents ranged from 2 to 7 amps with a variation in these numbers. So depending on when and how you measure it, you could be misled. But the bottom line here is that this screwdriver on several occasions were microscopically close to the component and the pin that was being damaged prior to assembly in the circuit board. So here's an example where you have to be careful how to interpret these isolated conductor limits. Okay, here's a game-changing myth. Circuit boards, the charge board event. There's a widespread misunderstanding. Often people assume that circuit boards are more robust than individual components. And it turns out to be just the opposite. Here's the truth. Circuit boards can be more sensitive than devices due to the much stronger discharge currents that are the direct result of the increased capacitance of the board, making it possible to store much more charge on ground planes and the various conductive elements of the circuit board. High levels of charge can be stored, and discharge currents of up to 25 amps are possible. So again, to emphasize what was said a couple of times, circuit boards can fail at lower voltages than standalone devices, or components on the boards, I should say. Again, 2020 does not cover the charge board event. Now, here's an illustration of what I'm talking about. Here we have a classic, in fact, this is an actual defect analysis from one of our clients. They gave us authorization to use it. And this gives you the various categories of failure, the diagnosed defects. And here's ESD, here's electrical overstress. But we now know that approximately 50% of the overstress failures are actually charge board event or cable discharge event failures. And about estimate of 20% of the no trouble founds are actually ESD related. Now, if we take these assumptions and replot the data, this is what it looks like. ESD moves from being down as a small contributor to failure to the #1 assignable cause of failure. So again, the charge board event is a game-changing discovery. And here is a way of illustrating that. This is a chart that comes right out of the Association Technology Roadmap from the year 2020. And it's, without getting to the details of it, what we're looking at here is a chart that tells us that there's a relationship between the physical size of the component to its ESD sensitivity. What we're saying here is you go from left to right, we're looking at physically larger components. As we go from top to bottom, we're looking at higher operating speeds. So if you have a large device at high operating speeds, it's likely to be down here in the lower right-hand corner where you're getting into the class 0 region. And now if we take that concept and move it to the size of a circuit board, it all, as you can imagine, gets worse. Meaning the board can store even more charge. Here's an example where we have a circuit board that Analog Devices has published papers on this. And they had failures coming back from the field of this device. Failure analysis initially indicated electrical overstress, but the circuit designer said it wasn't possible. It had to be something else. So they ended up doing this stress test of the board on a charge device model or CDM stress test equipment and repurposing it for the circuit board. So they charged the circuit board and then discharged it, and were able to duplicate the field damage. So the device was failing on the board, but not as a component. Here is an image of the resulting damage. On the left, we have a component with a typical charge device model failure point right here, a puncture and a gate oxide. And this image is at 4000x. On the right, we have another device with the image here at 200x. This is something you could see under a microscope. And you can see massive area of damage. Historically, that has always been thought to be electrical overstress. But we now know, with a lot of work from a lot of very capable people and special efforts, thanks to Analog Devices and Terry Welcher and his team at Bell Laboratories, for coming up with the better understanding. As I said a minute ago, we now know through organizations like Analog Devices that approximately half of the so-called overstress failures are actually ESD due to the charge board event. We're going to run a couple minutes late. I hope that most of you can hang on. I won't be going over much over the time, but I do need to let you know we're going to run a few minutes late. I'm going to show you this short video. Okay, here we have a circuit board and a person that's not grounded and an ESD event detector. Now, you see the number 3 on the detector. That means that prior to this activity, 3 discharges were reported by the ESD detector. So if the number changes, that will be additional discharge. So here we have an ungrounded person, a board being plugged into the system. With that single insertion, there were 8 additional discharges. So a total of 8 additional discharges with that single insertion of the circuit board. This was actually at a customer site in China, where we had been asked to come over and diagnose failures, and found this kind of activity. So that's a good example of the charge board event. Here's a little further understanding of it. This chart gives us a component with a current threshold of 5 amps, meaning if the discharge current exceeds 5 amps, it will fail. And the charging voltage in both cases is 250 volts. That is for the device alone, CDM, and then the board with the device on it. Here is the result of the component alone, charged to 250 volts, below the failure current level. looks fine. You put the same device on a board and charge it to 250 and discharge it, and you now have a peak discharge current of 9 amps and failure. So again, circuit boards can be more sensitive than individual components. Here is a cable discharge illustration. Cables charge easily, and if they're not grounded, and can discharge to the product causing damage. I'm going to do a quick demonstration here to illustrate that. Let me go back to the camera. Here we have a metal plate and an ESD event detector set up right next to it. Here we have a cable, and all I'm going to do is take it and rub it a little bit. Whoop, it just, you saw it triggered the events detector. Maybe you can see the lights flash on the event detector. I'll just manipulate the cable and we get more events. I'll do it one more time. And you can see there we had lights displayed quite a ways up the scale here, meaning they were strong discharges. So it's easy to create discharges, cable events. It's also easy to mitigate them. You ground the cable and the problem is resolved. Okay. Here is a further discussion on mitigation techniques. Here we're looking at two choices. One is to manage the voltage on the device, the sensitive product. And the other is to manage the surface resistance. Which one is part of S2020? Which one is included with requirements in S2020?
Surface resistance.
A great stab at it. Anybody else want to add a thought? Okay, thank you for stepping up for that. Unfortunately, it's just the opposite. 2020 we talked about the insulator, managing it and so on. We also said that there are no surface resistance requirements in 2020. Now, mats do have the proper surface resistance, and we do measure those items.
That's kind of what I was talking about.
Yeah, well, the requirements are in resistance to ground. It's a subtle distinction. It's not actually the surface resistance. In other words, you could have a steel work surface grounded through a 1 megohm resistor, and the resistance to ground will come out in the dissipative range. But the material itself.
Doesn't that violate NFPA 70E requirements?
I'm not familiar enough with that document, but I would say no. All of the safety, I assume it's a safety document. All of the safety, well, that's not quite true. As soon as you get into safety, you get into all kinds of subtleties. So let's not go too far there where we're over. I tell you what, let's come back to that after we finish the rest of the slides, in case others have to get back to their normal activities. Excellent question that I'd be glad to get into. Anyway, and to re-emphasize what I said a few minutes ago, Terry Welcher and I found that putting in surface resistance requirements often enables you to eliminate the need for ionization or many of the other methods that get involved. And they're less prone to human error. And we found them to be dramatically more cost effective. Less maintenance, less human error. And they work down to, once you use the right material, you can protect a 1 volt device. So there's a step function improvement a lot of value in really focusing on surface resistance.
Mhm. Ted, the one thing that I would also note here is that while lower device voltage is a strategy of the 2014 issue of 2020, it is no longer in the new version. So the answer to which one is 2020 in the new version is neither one of these is in 2020.
Tell me what you mean by that, Arnie. I'm not.
Well, that now that they've removed ionization as a mitigation method, how else do you take the charge off your insulators?
Well, in defense, and I don't know, we don't need to get into a lengthy debate here. I know what you're saying, but I would argue that you still have to manage the insulators, and they are referring us to other documents to learn how to do that. But
Right.
But it is one of our concerns for sure. I agree with you. Thank you. So we strongly advocate adding surface resistance requirements from decades of experience in a very grand scale. We have found it to be highly cost effective and much less prone to human error. Here is some objective evidence of that. This is a chart that many of you have seen repeatedly because we use it often, but it is a fact that here is a company that was 2020 compliant, had high failure rates, and with the introduction of surface resistance requirements, plus some other best practices, but the biggest difference was surface resistance requirements. The failures dropped sharply and approached zero as they continued to implement the more difficult best practices. Okay, that brings us to the end. Any questions we want to go back to or any new ones?
Yeah, I guess Brent from Canada, I just want to confirm with you. So, so the class 0 classification, I guess, will just be below 125 volts. I guess is that the plan? Like there's not going to be a finer grain, class 00 and 000. See, I was kind of hoping there'd be like a window, let's say, up to 50 volts, and that'd be maybe a class 000, so we can handle those type of components, the 100 volt. But I guess I'm dreaming. That's not something that's coming in the near term.
It's an important consideration, and there are many companies faced with that challenge. But to answer your question this way, 2020, the scope of it is 100 volts HBM, 200 volts CDM. The 125 is an insulator management requirement. So we want to make a distinction that the 125 is really a separate discussion. And the document is designed to handle 100, I'm going to repeat it, 100 volts HBM, 200 volts CDM, which does not include the more extreme sensitivities.
Right.
Will it be in the future? I hope so. Right now, we know it's very challenging, and the procedures to do that are complex. You can do it. We've done it many times, but it's complex and does not lend itself well to standardization because there are so many variables and case-by-case scenarios.
Yeah.
Hey,
I understand. Yeah.
hey, so Ted, this
Yeah.
is Matt Strick. This is Matt Strickland again.
Yep.
To follow up on Brent's statement there, within 2020 though, it does kind of address, right? Because there's a statement that does says for sensitivities that are less than, the 100 volt, 250 volt.
No, greater than.
Or greater than, I'm sorry. That additional measures, may need to be considered. That leaves that up to the end user, right? On how to go back and do that.
Yeah, good point.
And for the benefit of everybody on the call, there is another document that's coming out, which is TR19, which is that addresses some of the things that aren't in 2020. And so it'll be a roadmap for you guys on how to, it's called for ESD for high reliability. So there's additional measures that will be brought out, or that are brought out in that document, that hopefully it's going to come out sooner or later. So be on the lookout for that. And that might give you some guidelines and, you know, somewhere to, how do I say it, to go and look.
Excellent. Thanks a bunch. Because as technology is advancing, you know, the
Yep.
devices, you know, there's 0.1 micron devices now in the market. And, you know, it's just getting, you know, FET gates are getting thinner, and that's where the parts are heading there, you know.
Yep.
And it's trying to deal with that, and analyzing and predicting, you know, compliance to thresholds is a tricky game, you know. So any documentation coming out addressing these higher sensitive devices is always welcome, and we're always looking for that here at MBA in Montreal to help back up, you know, our analysis, you know, that things are all good for mission life and so forth. Great. Thank you very much for the advice. Thank you. Thank you.
You're welcome. And thank
When
you
can we
both.
get the 2020 document, new one?
I'm sorry, I couldn't hear that. Could you repeat it?
Sorry, this is Phil Bartels. I just wondering, when can we get the new version of the 2020 document?
Okay, the new version hasn't been released yet. It will be, I guess I don't know exactly when. If anybody on the call does know, speak up. But I believe that there are expectations of later this year, or maybe even early next year, I don't know. And then it'll be available as a free download on the association website.
Hey, Ted, this is Greg Heckler.
Yeah, hi, Greg.
How you doing?
Good, thanks.
Good presentation.
Thank you.
I was curious, you know, we've been doing a lot of walking tests for customers lately, and they're always frustrated with, you know, qualification requirement for temp and humidity. So I was wondering if anything's changing on that requirement for a pre-installed or an existing installed floor. You know anything about that?
Oh, yeah, that is, let's see here.
That's kind of frustrating.
Yeah. I'm trying to remember the details of it. Anybody want to jump in on that one? I don't want to misspeak. I have a strong sense of what's there, but I would rather have somebody jump in that. Anybody
Yeah,
remember?
Well, because as you know, I mean, most companies have already got their floors in this case.
Yeah, yeah, exactly.
So you can't really
Well,
do qualification.
I think maybe the saving grace there, as I think about it, is the new qualification RH requirement. In other words, you can qualify your floors based on the relative humidity in your building.
Yeah, I was thinking that exact same thing.
I think
Right.
now that I think about it, that probably would be the way to cover it.
Okay. All right. But if anybody knows, or I guess we'll find out if there's something when it's
I'm pretty sure
released,
that's
but-
the case. Yeah, I think that's
Okay.
Yeah, I'm all but certain on that one.
Okay.
I'm sure that would you can qualify it based on the RH in your building. So that would take care of it.
Great. Thank you.
That's one of the improvements.
I know
Ted, we
I've
have
always
a
had
chat
that.
question.
Good.
Go ahead, George.
I had that in my tailoring statement that we qualified our floor at the lowest RH our building would meet, and our auditor did accept that, so we are qualified.
Yeah.
Oh, good, excellent. And now you don't need the tailoring statement. Once the new version comes out, you'll be covered anyway.
That's nice, because you need a lot of objective evidence with the tailoring statement.
Right.
Yeah, you won't need it anymore. Remember, the tailoring is only if you're going outside of the requirements of 2020.
Exactly.
Mhm.
If you want to tighten within the, like, let's say you want, resistance to ground of ESD mats is 10 to the 9th. If you want to make a tighter limit of 10 to the 8th, you can do that without a tailoring statement. And there are examples in that new annex in the next version, the 2021 version.
Ted, we have a chat question. The question is, how do IEC 61000-4-2 ESD immunity levels correlate with HBM or CDM sensitivity?
Oh, that's an easy one. They don't. Any other question? Oh, I don't mean to be so glib, but it was a good opportunity. Yeah, they don't correlate. Yeah, system level stressing. In fact, there's a I don't think it's a standard. It's a test method. What is it?
HMM.
HMM. Is it a test method? I think.
I think so.
An
Well, it's
STM.
supposed to be a model, but so far it's just a test method.
Just a test method. Yeah, that came out and actually I think has added to the confusion. There is no correlation between system level stress testing and device sensitivities. Shavarka, a good friend and colleague of all of ours, he refers to HMM as the highly meaningless model. It's just not a good correlation, not a good way to go. Any other questions?
And none from me, but I just want to thank you, Ted. Every time I listen to you, there's so much I learn, I'll tell you. And you know, I just, there's so much to learn from you. Thank you so much for these sessions. I just want to tell you, up here in Canada, you know, you really are the expert, and we look forward to your briefings and all your information on this topic, complex topic of ESD. Thank you so much for today's time. Time well spent for sure. Thank you.
Oh, thank you. You're welcome. I really appreciate the feedback. We enjoy sharing what we've learned.
Thank you.
And the IEEE Society also thanks you for presenting to support our group. The chapter always enjoys having you speak for us.
Oh, thank you. And I really appreciate the collaboration. And on behalf of the Northeast chapter, we thank you for your support and continued collaboration.
Look forward to the next time.
Thanks. Thanks, everybody. Appreciate it.
Thank you. Thank you, Ted.
Thank you, Ted.
Bye.
Thank you.